Right. Let's begin our afternoon session. Our next speaker needs no introduction. For many years, he has been dazzling us with beautiful ideas and insights coming from quantum field theory that have kept several generations of mathematicians busy. And more recently, with his co-authors, he found the links between the Langlands program and dualities in quantum physics. So it's a great pleasure to have Edward Witten from Institute for Advanced Study, who will talk about mirror symmetry and geometric Langlands.
Thanks for the kind introduction, and I guess I can thank the organizers for inviting me, since I'm not one. So I want to start by explaining why it's natural to associate geometric Langlands to a quantum field theory specifically in 4 dimensions. So also I want to say, I know the audience is very diverse. So there will be occasionally some big words thrown in that will make more sense to some than others. You're supposed to ignore them when they come along. So geometric Langlands involve statements about a Riemann surface C, which for us is simply a 2-manifold. But the basic statements are not statements about numbers or vector spaces. They're statements about something more abstract called categories. And here we have to remember what quantum field theory does. A d-dimensional quantum field theory associates to a closed d-manifold M sub d a number, the partition function. It associates to a closed d-1 manifold md-1 a vector space, which is the space of physical states. And to a d-2 manifold, it associates a category, which you can think of as a category of boundary conditions. For practitioners of quantum field theory in 4 dimensions, the first 2 steps in this hierarchy are familiar, and the third one is slightly less familiar. Where physicists have used the third step in the hierarchy most is for d equals 2, where in string theory, one has branes, which arise as boundary conditions in quantum theory, and although this isn't the language physicists usually use, mathematicians speak of a category of branes. And that's a special case of the fact that in general, in d dimensions, quantum field theory attaches a category of boundary conditions to a closed d-2 manifold. Now, in geometric Langlands, we're supposed to have a category to a 2 manifold. So we want d-2 to be 2. And a small amount of arithmetic reveals that d should be 4. So to make a statement with the general nature that we have in geometric Langlands, we should start in 4 dimensions. Now, what kind of quantum field theory are we going to do in 4 dimensions? Well, all the particle physicists will tell you that the interesting ones are gauge theories. Those are, roughly speaking, the only quantum field theories that really work in 4 dimensions. But there's another reason we should start with gauge theories. Well, first of all, I'll give you another naive reason before I go to the reason on the next page, which is more technical. Another naive reason is that geometric Langlands involve statements about groups. And although it's not quite the only way that groups come into quantum field theory, gauge groups are conspicuous, a conspicuous way for groups to enter. Now, if we want to say something more technical, so geometric Langlands involve statements about, roughly speaking, the moduli space, but really the stack of G bundles, or the analogous stack of flat bundles for the dual group on the 2 manifold C. Since we'll be doing gauge theory, so here I differ from the notation most often used in geometric Langlands. G is a compact Lie group, which will be the gauge group of our theory. And when I'm interested in its complexification, I say so. So this symbol denotes the complexification of G. So where would stacks come into quantum field theory? What do physicists do, which is all about stacks, without saying so? Well, as explained 30 years ago by T. and Budd in a paper that Nigel mentioned in the last talk, the natural field theory model of the stack of all bundles is just the space of all gauge fields acted on by the gauge group. In other words, well, to be technical, you fix a G bundle over C, remember, is our Riemann surface. You fix a G bundle E over C of a given topological type, and you consider all possible connections on that bundle. So that's a model of the stack of GC bundles. The reason is the following. On a Riemann surface, as opposed to a variety of higher dimension, every connection defines a holomorphic structure. That's because we take any connection, and just as in, I think, Nigel's talk, we write it as the sum of parts of 0, 1, and 1, 0, but on a Riemann surface, the 0, 1 part always squares to 0, because there isn't any room for a 0, 2 part, dimensionally. So every connection endows our bundle with a holomorphic structure, and every holomorphic bundle of the given topological type arises this way. So in fact, the quotient of the space of connections by the group of complex value gauge transformations is the set of isomorphism classes of GC bundles. And you can think of the pair, the space of connections with an action of the gauge group, as being a model for the stack Bun G. I should maybe just say one thing, which is that even though our connections are unitary, the complexified group acts on the space of connections. That's because we transform Nabla 0, 1 by a complex valued gauge transformation, but the overall connection is supposed to be real, but Nabla 1, 0 is just the complex conjugate of Nabla 0, 1, so we make the complex conjugate transformation of Nabla 1, 0. So it's not a symmetry of gauge theory, but it's an operation that makes sense on the space of connections. So in a sense, this is more natural than any customary model, any customary description of the stack of G bundles. There isn't any nice, I don't know whether there's a finite dimensional model for the stack of G bundles, but there is presumably not a canonical one. Here, at the cost of going to infinite dimensions, there's a completely canonical model for the stack of G bundles as the quotient of this infinite dimensional space by the infinite dimensional gauge group. Now, to do geometric Langlands, we're supposed to, well, there's going to be differential graded stuff. So in particular, there's a differential, which for us is a symmetry whose square is 0, but it's a fermionic symmetry. It maps even stuff to odd stuff and vice versa. So a field theory that's going to have odd symmetries is a supersymmetric field theory. So our four-dimensional theory, which is going to be a gauge theory because that's what there is in 4 dimensions, and also because it's supposed to involve gauge groups, is going to be a supersymmetric one. So being a supersymmetric one, it has got a bunch of odd symmetries. And one of these odd symmetries will be the differential of geometric Langlands. So what supersymmetric gauge theory are we going to do? Well, first question you might ask is, what ones are there? And physicists know all about that because that's a decent chunk of what we study. So one simple thing I can tell you is that for every G, there's a maximal supersymmetric gauge theory, one that has the most possible symmetry, and that turns out to be the right one for geometric Langlands. So it's called n equals 4 Super-Yang-Mills theory. So this theory is determined by the choice of a compact simple Lie group, G, as well as a complex parameter, which is called the coupling parameter, that takes values in the upper half plane. So it's got all kinds of fascinating mathematical and physical properties, this theory. For example, well, okay. I won't mention, I'll limit myself to the examples that are on the slides. So it's determined by the choice of a gauge group and also a coupling parameter, but there's a classical equivalence, which is related to the integrality of the second Chern class. If I were to explain exactly how one constructs this theory for given tau, then you'd see that because the second Chern class is an integer class, that results in a periodicity under tau going to tau plus 1. But there's something much more interesting, which is a quantum equivalence that's Monton and Olive duality or S duality or electric magnetic duality. Those are some of the names it goes by. That exchanges G with G dual, where G dual or G check is the Langlands or Goddard-Neutz-Olive dual group. In this audience, most of you know how Langlands introduced the dual group, and later on I'll recall how Goddard-Neutz and Olive did. And NG is an integer that's the ratio of length squared of long and short roots. So it's 1, 2, or 3 depending on G. And finally, so just like the G theory has a tau parameter, the G check theory has a tau check parameter. So tau check is the coupling parameter of the n equals 4 theory with the dual gauge group. And the theory with the dual gauge group also has an integer valued second Chern class, so it has a classical symmetry that shifts tau by 1. So there's an infinite discrete group that acts on the tau plane or the tau dual plane. Now, for us, the real star of the show is the quantum duality symmetry that exchanges the group with the dual group and also exchanges the two coupling parameters. So it's called electric magnetic duality. It exchanges ordinary electrically charged particles with magnetic monopoles. And it's extremely important in modern theoretical physics. For example, it's related to the mechanism for confinement of quarks in atomic nuclei. And it's a prototype. The existence of this duality symmetry in this gauge theory is a prototype for the modern understanding of the strong coupling behavior of string theory. Now, comparing to geometric Langlands, there's a perfect symmetry between the two descriptions. One description is constructed from G, and the other description is constructed from G dual, and the two theories are constructed in exactly the same way. So there's a perfect parallelism between the two sides. People who work in the Langlands correspondence will not, by other methods, will not expect this because the usual formulation is very asymmetrical between G and G dual. The correspondence is often called a duality, but it's a duality between one construction from G and a quite different looking construction from G dual. Whereas here, at the fundamental level, we have a completely parallel construction, and the fundamental duality symmetry merely exchanges the two groups while inverting the coupling parameter. So the question you might ask me is, if this is the duality that underlies geometric Langlands, why does it look asymmetrical? I'll go in more detail later, but the reason is that you ask a question that breaks the symmetry between the two sides. But I thought I would tell you that it's not only in math that the symmetry is sometimes lost. It's also, physics is in practice not usually as perfect as the mathematical model I'm describing. So perhaps the most important application of this general circle of ideas in physics is to Quark confinement, but that actually is an example somewhat like other approaches to Langlands. There are two different dual descriptions, one good for one class of questions and one better for a different class of questions, but there's not a simple symmetry between the two descriptions. So in that sense, the real world problem of Quark confinement is much more similar to other approaches to the Langlands correspondence than the highly idealized mathematical model I'll be telling you about today. Well, as I've already alerted you, it's the electric magnetic duality symmetry that exchanges the two groups that leads to geometric Langlands duality. So that's actually, you see, as a physicist, I claim that that's geometric Langlands duality while standing on one foot. Of course, the hard part is to spell it out and explain precisely what questions you ask, where when you work out this duality in practice, you arrive at the traditional statements, such as we've heard in previous lectures. Now, the usual geometric Langlands correspondence actually involves questions that don't depend on tau or tau dual. So in that context, you can think of the duality as merely exchanging the two groups. There is a generalization of geometric Langlands that people sometimes call quantum geometric Langlands. I'm not a fan of the name because to me the whole theory is best studied in the context of quantum field theory. But anyway, there's a generalization that people call quantum geometric Langlands that does depend on the two tau parameters, and then the infinite discrete duality group is important. But we won't be discussing this generalization today. So, as I said before, from this point of view, the basic formulation is completely symmetrical between the two groups. But the symmetry will be broken by the choice of questions. So, I mean, there are all kinds of things that I should tell you about n equals 4 super Yang-Mills theory, and it really should follow a couple of courses on quantum field theory. But one thing which is so basic I should mention it is that this theory is conformally invariant. So that means that to formulate it on a 4 manifold M4, we require only a conformal structure as well as a spin structure, not a Riemannian metric. Now, on four-dimensional Minkowski spacetime, so that means that, the usual quantum field theories studied in particle physics are naturally formulated in Minkowski spacetime, and then they are invariant under the motions of Minkowski spacetime that preserve its pseudo-Riemannian metric. But here we've got a conformally invariant theory, so it's invariant under a larger group of conformal motions. In 4 dimensions, the group of conformal motions is SO24, but to allow for spin, we take its double cover, which is SU22. However, we're dealing with a supersymmetric theory, so its automorphisms will not just be SU22, but a supergroup that extends this. And for n equals 4 super-Yang-Mills, this supergroup is the simple supergroup PSU22/4. So, roughly speaking, that you could think, except for the P, you could think of that as a space of odd matrices that act on a space of dimension 4/4 with 4-dimensional even rank and 4-dimensional odd rank. The off-diagonal blocks are the odd generators of the supergroup. So the diagonal blocks are the maximal bosonic supergroup, which is SU2, 2 times SU4. So SU22 is the conformal group of spacetime, but SU4 acts trivially on spacetime. So what is SU4? Well, physicists call it a group of R-symmetries, but that's just a name. For mathematicians, I'll give you an example of a group of R-symmetries. So on a Kähler manifold, there's a SU2 symmetry of Lefschetz that acts on the cohomology of a Kähler manifold. Well, it's usually called SL2. If you think of the Kähler manifold as just in a world where you would deal with harmonic forms, the group that acts naturally on the harmonic forms is SU2, the real compact real form of SL2. Anyway, in this line of work, the theory of differential forms on the manifold is a one-dimensional quantum field theory, where the one dimension is time, usually suppressed in the mathematical treatment. And the group of symmetries that acts trivially on the time is the Lefschetz SL2. On a hyperkähler manifold, Lefschetz SL2 is extended to an SP4 that acts on the cohomology of a hyperkähler manifold. And that's still one-dimensional quantum field theory. Here we're in four-dimensional quantum field theory, so things are a little bit richer. And instead of being SL2 or SP4, the group of R-symmetries is actually SU4. Now, PSU22/4 might seem like a rather big supergroup, but it's just barely big enough that you can fit geometric Langlands in there. So I said at the beginning that we were discussing the essentially unique theory, supersymmetric gauge theory with gauge group G, with the largest possible supersymmetry algebra. We could use a smaller supersymmetry algebra, for example, if we wanted to head for Donaldson theory instead of geometric Langlands. But geometric Langlands barely fits in this theory. It doesn't fit in the smaller ones. So there's a procedure, which I won't explain in detail, of twisting a physical theory to make a topological field theory. And we make use of some of the bosonic symmetries in the twisting, but we're left over with something. So one thing we're left over with is a particular odd generator and also a particular even generator. Both the even generator is part of the R-symmetry group. So the odd generator becomes the differential of geometric Langlands, and the even generator gives us a Z-graded theory. So actually, the Z grading comes from a subgroup of the SU4 R-symmetry group. That was also true for Lefschetz, of course. The Lefschetz, it's not true for Lefschetz. Sorry. Okay. I better not. Okay. There's a U2 that acts on the cohomology of a Kähler manifold. Perhaps if we go to the hyperkähler case, the assertion I blundered into would be correct. I think it's SP4 rather than SP4 times U1 that acts on the cohomology. And then the grading by degree is part of the R-symmetry group. So in general, n equals 4 super-Yang-Mills is definitely not a topological field theory. Most physicists who study it are not thinking about topological field theory at all. By far. Well over 99% of the literature on this theory does not deal with topological field theory. So it's this theory of physical propagating fields. But you can get a topological field theory by picking an odd generator Q of PSU22/4, chosen so that Q squared is 0, after which, roughly speaking, you pass through the cohomology of Q. Or more exactly, you think of Q as a differential and constructing a differential graded theory. So there are inequivalent choices of Q, and so there are several different topological field theories you can make. So you have to pick Q so that the response of the theory to a change in the conformal structure is Q exact. So I won't try to explain what that condition means in practice, but there are 3 inequivalent ways to achieve it. They're all interesting. For example, one of the 3 was studied by Vafa and me, and we showed that a generating function for Euler characteristics of instanton moduli spaces was going to be a modular form. And another of the 3 theories leads to geometric Langlands. So it's the choice of Q that broke the symmetry between G and the dual group. Now, I can't possibly explain everything today, but I want to give a few hints. And the best way to give a hint I could think of was to tell you what are the fields on the theory and what is the condition for a set of fields to be Q invariant. Which is, you should think of it as being a semi-classical approximation to computing something, like describing an object in a category, calculating a space of morphisms, or doing something. For physicists, finding a space of physical states, the approximation is to find a classical state that's Q invariant. So what are the relevant fields? Well, in the description by the dual group, the relevant fields are a complex valued connection. It's very important that this is complex. We started with the compact gauge group, but by the time we twist in the G-dual description, we end up with a complex valued connection on a bundle whose structure group is the complex gauge group. And it comes together with an endomorphism. I wrote endomorphism with M, but that should have been endomorphism of the bundle E, understood to be in cohomological degree 2. In other words, under the Z grading, which came from a distinguished SO2 in the R symmetry group, it has degree 2. And for Q invariance, they have to obey some equations which say that the curvature should vanish, and the endomorphism, which should have been sigma V here, is covariantly constant. So the classical picture is a flat bundle together with the symmetry of it. If the bundle is irreducible, then the endomorphism will have to be 0. So that's a situation that's often considered. Roughly speaking, on a sufficiently rich 4 manifold, a generic flat bundle will have no non-zero endomorphisms. So often in practice, sigma will be 0. So this was the description in terms of the dual group. In the description by G, the fields are connection A on a G bundle. Here there's no complexification. The structure group is the compact form. And also a field phi, which is a 1 form valued in the adjoint bundle. It's actually the same structure that Hitchin talked about in his last lecture, except that we're in 4 dimensions instead of 2. So we'll get a more complicated set of equations, but they can be specialized to the equations Hitchin told you about. So they obey a system of elliptic differential equations. So what I'm writing down is the condition for Q invariance. The condition for a set of fields to be invariant under the differential that we use in different geometric Langlands is that the fields have to obey a set of elliptic differential equations. Elliptic means elliptic modulo the gauge group, and star is the Hodge star operator in 4 dimensions. So there's also an endomorphism sigma of degree 2 in this description, and it's now related to equivariant cohomology. So an approximation to what you do is that you study some kind of cohomology of the space of solutions of these equations, except, if the gauge group acts freely, you could ignore sigma. But when there are solutions that don't completely break the gauge symmetry, you should better do equivariant cohomology rather than ordinary cohomology, and then sigma can come into play. So one thing which actually, it's a fun story, but we don't have time to go in that direction today, is that these same equations I'm talking about here are also important for a certain description of the Jones polynomial and Kovanov homology using gauge theory. In fact, using basically the same gauge theory ingredients that lead to this story involving geometric Langlands. So these equations are also closely related to Hitchens equations and Higgs bundles, and that's how Higgs bundles will make an appearance. So the quickest way to say that is that if you look for a solution of these equations, those are equations, let's say, on R4. You could pick a projection of R4 to R2 and ask for a solution that's a pullback. And then you'll get Hitchens equations. So Hitchens equations are the two-dimensional specialization of those equations in that sense. Now, as I've already remarked, in geometric Langlands, we're going to study the category of boundary conditions. The boundary of the 4-manifold is going to be a 3-manifold. But geometric Langlands is usually formulated for a time-independent situation, which means that, well, one of our coordinates will be r, or space-time will be the product of r, parameterizing the time, times something. And in particular, the boundary will be the product of the time, r, times a Riemann surface, C. C is the Riemann surface in which we do geometric Langlands. So I've drawn here a picture with the time suppressed. This is a picture at fixed time. I've simply tried to draw a 3-manifold whose boundary is a given Riemann surface. So we're interested in the category of boundary conditions, so let's discuss some boundary conditions. Well, in the G-dual description, which deals with flat G-dual bundles, an obvious type of boundary condition is to simply specify a flat G-dual bundle on the boundary and require that the boundary values of the fields coincide with that flat bundle. So an obvious example of a boundary condition is to pick what people in geometric Langlands call a G-dual local system, a flat bundle on C whose structure group is G-dual sub C, except people in geometric Langlands would usually call it just G-dual because they wouldn't have started with the compact group. So these traditional Dirichlet boundary conditions, or at least the simplest ones, would say that the fields are 0 on the boundary. Here, that would correspond to a boundary condition associated to the trivial local system. Instead of saying that so even in elementary textbooks on analysis, instead of taking the Laplace equation with 0 boundary conditions, you can take the Laplace equation with any specified function and look for solutions of the Laplace equation with that function on the boundary. So that's a kind of shifted or twisted version of Dirichlet boundary conditions. Here, we twist by specifying a flat bundle on the boundary and asking that the fields coincide with that flat bundle. It's less obvious what are natural boundary conditions in the G description or how to compute the dual of a given local system of the dual group. It's actually very powerful to first understand what happens if we split off not just one factor of R, but 2 factors of R. So we take our 4-manifold to be the Riemann surface C that we're interested in, times R2. So you can think of that as being merely that we take this picture, but far away from the boundary. I drew C times what might have been R plus, a half line. If we're far away from the boundary, it just looks like C times R. But I've suppressed the time in drawing this picture, so it would really be C times R2. So C times R2 just means we're trying to understand what happens far away from the boundary, and then we'll come in toward the boundary. So the sentence I just displayed is what I just said. We first discuss what happens far away from the boundary, and then it'll be easier to understand how the duality acts on boundary conditions. Asking what happens on R2 times C is the typical kind of problem that physicists study, actually. So we compactify on C, or we turn on a magnetic field, or we do something, and then we ask what happens at long distances. So on R2 times C, the theory is described at long distances. That means on a length scale large compared to the size of C, by a conformally invariant theory on R2. That's a highly non-trivial statement, because generic quantum field theories aren't conformally invariant. Conformally invariant ones are very special and often very important. In this case, we get conformal invariance back at long distances because there's still a lot of supersymmetry, even after compactifying on C. So the theory is what physicists call a sigma model, a supersymmetric theory of maps from R2 to what I'll call M sub H of C and G. That's Hitchin's hyperkähler moduli space of G bundles on C. Okay, this statement is true for both groups. Regardless of whether the group was G or G dual, we get the appropriate Hitchin moduli space. So the statement I've just made was first shown by physicists in the 90s, and then the mirror symmetry that I'll mention in a second was first discussed by Housel and Thaddeus, who, among other things, were giving a very simple example of earlier ideas by Strominger, Yell, and Zaslow. But the rough idea is that, So if you're far from the boundary, if you're a physicist, the one important question to ask is what happens on a length scale large compared to the size of C? In geometrical Langlands, there's no length scale. So what that means is that you're always at lengths large compared to the size of C. But when you formulate it as a physicist, starting from the physical problem, you do have to explain that you're going to long distances. And then at long distances, you almost have you basically have a solution that's almost a pullback from C. And the solutions that are pullbacks from C are the solutions of Hitchin's equations as he described them in the last lecture before lunch. So anyway, that's an intuitive idea of this assertion that the long distance approximation is a sigma model whose target is the Hitchin moduli space. Now, the Hitchin moduli space for both G and G dual both have Hitchin fibrations. And the base of the Hitchin fibration is the same for the group and the dual group. According to Strominger, Yell, and Zaslow, mirror symmetry is T-duality on the fibers of a fibration, a special Lagrangian fibration, which usually is difficult to exhibit explicitly. But the point of the paper of Housel and Thaddeus, in part, was that in this case, well, it has to do with what you also heard in the last lecture, that there are many different complex structures going on at once. The whole picture is a little bit too complicated to explain right now. But the Hitchin fibration, which is a holomorphic fibration in one complex structure, from a different point of view, is a special Lagrangian fibration. So we can understand mirror symmetry much more explicitly than we usually do by T-duality on the fibers of the Hitchin fibration. And roughly speaking, geometrical Langlands duality is the mirror symmetry between the B model of one moduli space and the A model for the dual group. So the claim is that S duality in 4 dimensions simply reduces in 2 dimensions to the mirror symmetry between these two models. The reason I said roughly speaking is that although this description captures a lot, it's not precise enough for all the delicate questions that are usually asked in geometric Langlands. Now, there's another important part of the story which I won't explain today. I'm just stating it on this page. And Ed Frankel stated it toward the end of his talk. So I gave a simple example of a G-dual boundary condition. It corresponds to picking a local system. But a local system is just a point in the Hitchin moduli space. So our simple example on the what's sometimes called the Galois side of the geometric Langlands correspondence was to pick a G-dual local system, which means a point in Hitchin's moduli space. When we make T-duality on the fibers of the Hitchin fibration, a point is mapped to the whole fiber that contains it, endowed with a flat line bundle that depends on which point you started with. I should have had a picture. I should have made this into a slide, but I didn't. So here I'll just very briefly sketch the Hitchin fibration. And now we've picked a point over it in the G-dual description. In the G description, we have a different fibration over the same base, but importantly, it's over the same base. So the dual of that point is the whole fiber here. But which point it was goes into what flat line bundle this fiber is endowed with. So a point is mapped to an A-brane that's supported on a fiber of the Hitchin fibration. So at least at the simplest level, that's the answer to the question, what's the dual of a B-brane supported at a point? However, I did not get the answer in the language that people like in usual approaches to geometric Langlands. I expressed the answer as an A-brane. And instead we want a D module. And as Ed Frankel kind of loosely indicated, because of the close relation of the Hitchin moduli space to the cotangent bundle of bun G, in this situation, A-branes have an alternative interpretation as D modules, and that leads to the usual formulation of geometric Langlands. Well, there's another thing which we really should try to say at least a few words about. So the point of the whole story in Langlands correspondence is to show that the dual of a B-brane supported at a point is a Hecke eigensheaf. So I'll kind of tell you what that's true without quite telling you what it meant, assuming that various bits of what I'll say will be understandable to different people. So the key point is something that actually is quite important in physics, the duality between Wilson and the 't Hooft line operators, or in other words, between parallel transport in G-dual gauge theory and a singularity of a certain type in a G gauge field. So all I've drawn in this picture is a curve. It could be a closed curve, or maybe it ends on the boundary. We don't usually want it to end in the interior of the manifold. But I've just drawn a piece of a curve in a 4 manifold, without on this page telling you what we're going to do with it. Now, on the next page, I'll tell you two things that we could do. I think it's the next page, which are going to be dual to each other. We can do one of two things. In the dual gauge theory, we pick a representation of the dual group, and then, well, the way mathematicians say it is that we take the bundle associated to E dual in that representation, and that gives us a G dual bundle over M, and then we perform parallel transport. If we have a section of that bundle restricted to the line, and we can parallel transport using the connection restricted to L. So when you do that in the context of quantum theory, it's called a Wilson operator. And the physical interpretation is that L is the world line. The world line means the path in space-time followed by a point particle. So a point particle is a point at a given time, but in space-time, its trajectory will be then a curve, called the world line. So the physical interpretation is that L is the world line of a charged particle in the representation, in a chosen representation of the gauge group. So we decided what was going to be the world line of this particle. That means it's not one of the particles described by the theory. It's an extra particle that we added as an impurity. So I claimed at the beginning that there's a complete S-duality between the G-dual and G descriptions. So anything that we can think of in one description has to have a dual in the other description. So in this case, the dual of parallel transport is known. It's the 't Hooft operator, and its definition is rather interesting. In G gauge theory, well, you have to remember that we're in 4 dimensions. So if you have in 3 dimensions, if you think of this piece of chalk as a line, its link would be a circle around it, S1. But in 4 dimensions, the link of a curve would be a copy of the 2-sphere. So we're going to specify a singularity that a G gauge field should have along L, and we'll specify it by saying that if you take a very small 2-sphere, no matter how small, I'm going to specify what the gauge fields look like on S2 in a moment. And that'll define a singularity because the choice I'll make will be one that won't extend over the interior. If you remove L from space-time, then I'll just explain what a gauge field should look like, but it will be singular along L because it'll have a curvature integrated over S2, which doesn't go to 0 when S2 shrinks. So, well, what are we going to do? Well, S2, first of all, there's a conformal structure on space-time, so S2 has a conformal structure. So it's actually a complex Riemann surface, CP1. And as I told you before, every G bundle describes a G sub C bundle, a homomorphic G sub C bundle. And the 't Hooft operator is defined by specifying the holomorphic type of this bundle. The physical interpretation is that the singularity represents a magnetic impurity of specified charge. the charge is the holomorphic type of the bundle. Sorry. So in the Langlands correspondence, an important fact is that representations of the dual group correspond in a natural way to isomorphism classes of G bundles over CP1. It's not always stated that way. But G bundles over CP1 can be classified, and if you use that classification, you'll end up, if you're not accustomed to stating the Langlands correspondence this way, you'll find that if you use the classification of bundles on CP1, you'll probably end up with a version of the statement that you are accustomed to. As a statement about electric and magnetic charges in four-dimensional gauge theory, the statement that the dual of parallel transport in a given representation is given by this other singularity goes back to Goddard, Neutz, and Olive, although it was clarified much more recently by Kapustin. So now, remember, in geometric Langlands, the dual of a local system is supposed to be a Hecke eigenchief. And without explaining all the details, I'll say that the Hecke eigenchief property comes from the duality between the two types of line operator. In the situation depicted, in the situation where L is near the boundary, I've suppressed time in this picture. So you imagine that I've sketched a 3 manifold with a point in it. You take the product of that times time. So I've drawn L as a point, but it really is a line running in the time direction. And see, in the parallel transport description, what we would have at this point L is just the fiber at that point of the associated bundle to the given representation of the dual group. But in the G representation, we'd be insisting on a funny singularity. And that funny singularity will cause the gauge field along C to undergo a Hecke modification when you jump past the singularity. So since I've lectured about this many times before, and some of you have heard it, and time is running short and there's a lot to do, I won't explain details, but you could take the gauge fields here, they would jump, so you could take a copy of C at the boundary, but you could take a copy of C at some place else. And as you move in toward the boundary, when you cross the singularity, the holomorphic, there's a jumping of the holomorphic structure, which gives what people in geometric Langlands regard as the geometric analogs of Hecke modifications. When I was interested in trying to interpret, in terms of quantum field theory, geometric Langlands, well, there are plenty of things I've never managed to do and are still completely unclear, but among things that eventually became clear, the hardest one for me to understand at least, was the fact that geometric Hecke operators simply correspond to what physicists call 't Hooft operators. So a B-brane supported at a given local system is an eigenbrane. Well, I didn't know what the right word is here. That's why they're question marks. They're not typos. So in geometric Langlands, an eigenchief has an eigenvalue, which is a vector space. So here, the eigenvalue, or eigenspace, is a vector space by which the brane will be tensored if you introduce a charged particle at the point L. And dually, the A-brane will be a Hecke eigenchief. That's a general prediction of the duality. And in terms of A-branes, you can verify it fairly explicitly using standard properties of the Hitchin fibration. Rather than explaining all this in more detail, I want to describe an approach in this framework to the universal kernel of geometric Langlands. And here I'm following ideas explained in my paper of a few years ago with Davide Gaiotto. So we're going to describe the universal kernel in a universal sense. So what is the universal kernel as understood conventionally? You fix a Riemann surface C, and you want a procedure that will transform any sheaf in the dual gauge group into an object in the gauge group G. So in our language of B-branes and A-branes, you want a universal mapping from B-branes to A-branes. But as usually formulated, the notion of the universal kernel, you're allowed to pick a Riemann surface C. But we're actually going to be more universal. We won't pick C. We just divide space-time into two halves. So I'm not much of an artist, but this picture represents R4, or Minkowski space R31, but I've divided it on a codimension 1 plane, which you can think of as R21, and I do gauge theory with gauge group G and coupling parameter tau. I hope that looks like a tau. But since there is a duality, I could explicitly use a dual set of variables over here, which would be the dual group and also the dual coupling parameter. But if I literally do that, we'd have trouble saying anything, because, you see, remember the dual coupling parameter is -1 over the dual parameter, and to get a simple semi-classical description, which one should aim for if one wants to be able to make concrete statements, you want im tau and im tau dual to be large. But they can't simultaneously be large if they obey that relationship. So that's actually what makes geometric Langlands and the quantum field theory duality that we're talking about today both difficult and interesting. However, you can modify the problem. You can verify tau and tau dual independently at the cost of reducing PSU2/4 to a subgroup. The largest subgroup you can retain is actually OSP4/4. A maximal bosonic subgroup of which is SP4 times SO4, where SP4 is the group of conformal motions that fixes the plane. If all we did was to make duality on half of the variables, it's just a change of notation, and we haven't broken any symmetries. But when we vary the parameters independently on the two sides, we're really changing the problem, and we're only left with conformal motions that fix the plane on which the jump occurred. So we only see three-dimensional conformal symmetries and a smaller R symmetry group. So if we take the imaginary part of both tau and tau dual very, very large, the gauge groups are weakly coupled and semi-classical, and the subtlety all resides at the interface. Supported at this interface is a three-dimensional superconformal field theory. This is the third time I've told you about a superconformal field theory today. We started with one in 4 dimensions. We reduced on a Riemann surface and got one in 2 dimensions. And we now are putting in this domain wall between two different descriptions and finding a superconformal field theory now in 3 dimensions. But this superconformal field theory has a symmetry which is the product of the symmetry of the dual group times the symmetry of G. The way physicists would say it is that G dual gauge fields on the left and G gauge fields on the right have been weakly coupled to a superconformal field theory at the interface between them. So Gaiotto and I called this theory T of G. So you can object that our notation is slightly asymmetrical because we could have called it T of G dual. That's related to something I think I'll tell you in a second. Okay, anyway, since it'll be a while, I'll just say now that there's a mirror symmetry between T of G and T of G dual. So although my notation is asymmetrical, there's actually a non-trivial automorphism that restores the symmetry. Now, since I described T of G in a slightly abstract way, which might have sounded like all I was saying was that, well, if there is a duality, we must be able to do something. Slightly abstract. But, you see, there was a non-trivial statement, which was that when both tau and tau dual went to the semi-classical region, we were left with a superconformal field theory on the interface. And that statement has a lot of information. So I want to make it sound a little bit more concrete. So I'm going to tell you the most interesting things I could think of to tell you about T of G inside 2 minutes. So one thing is that T of G for groups of type A can be constructed as a quiver gauge theory. So I'm hoping a lot of you at least know what a quiver is. So these are circles, and this is a square. Sorry for the poor drawing. This is a circle here. So that's a very particular linear quiver there. And so in the math literature, there's really a lot of work on hyperkähler manifolds associated to quivers, perhaps starting with Kronheimer and Nakajima. But for physicists, you can construct from a quiver not just a hyperkähler manifold, but a superconformal field theory in 3 dimensions, which, among many other things, has got a second hyperkähler manifold associated to it. And one of the important things to tell you about would be the moduli space. I must have turned this off. Okay. One of the important things to tell you about would be the moduli space of Acura of the theory. But maybe first I'll tell you briefly about mirror symmetry in 3 dimensions, which has been explored by both mathematicians and physicists in the papers I've indicated, plus a lot more physics papers. So in this case, so to appreciate better what I'm going to say, one should know something that not very many mathematicians are familiar with about mirror symmetry in 2 dimensions, which is its relation to an outer automorphism of the superconformal group. I'm afraid there isn't really time to explain it, but there's a similar story in 3 dimensions, where the R-symmetry group SO4 has an outer automorphism that comes from a reflection of one of the 4 coordinates. And this is actually extends to an outer automorphism of OSP 4/4. So SO4 is actually locally a product of 2 SU2 groups, and the outer automorphism exchanges them. So finally, I'll say that in this context, mirror symmetry exchanges G and G dual while also exchanging the 2 SU2s. So in other words, the mirror of T of G is T of G dual. And one of the SU2s is going to be the Arthur SL2, although which it is depends on our choice of differential and the way we broke the symmetry between G and G dual. So the moduli space of Acura of the theory is going to be a conical hyperkähler manifold with an action of a lot of stuff. The group and the dual group act, and so do the 2 SU2s. And unfortunately, here it's important to know a bunch of things that we don't have much time for. So many naturally occurring objects that are often regarded as complex symplectic manifolds with a C-star action that rescales the symplectic form are actually also naturally studied as hyperkähler manifolds. In fact, Nigel Hitchen went some way down the line toward explaining this in his last talk, although he didn't go to precisely this. So for the hyperkähler manifold, C star, which is U1 times the positive reals, is extended to SU2 times the positive reals, where SU2 rotates the complex structures. So if you pick a complex structure and you're only interested in that one rather than the hyperkähler structure, then you only would see the subgroup of SU2 that fixes a particular complex structure, and that's U1. So from a hyperkähler point of view, the group that acts is actually the quaternions. If you think about it, SU2 times the positive reals is the group of non-zero quaternions. But from a complex point of view, the group that acts is the non-zero complex numbers. So there are a lot of examples of this, but the examples important to us are due to Kronheimer, the nilpotent orbits in the Lie algebra of a complex simple E group, and also the corresponding Slatowy slices, all have this kind of hyperkähler metric with an action of the invertible quaternions. With this understood, so now when I refer to an orbit, I really mean an orbit in this hyperkähler sense. So the moduli space of vacuum of T of G is naturally embedded in the product of the two nilpotent cones of the 2 Lie algebras, where on the nilpotent cone of G dual, there of course acts G dual and also an SU2 group that I'll call SU2X. And on N, there maps G together with the other SU2. So N has many strata. The top strata are what physicists call Coulomb and Higgs branches. They are one cone times the origin and the other cone and vice versa. The lower strata are products of orbits, where the orbits are certain nilpotent orbits in the 2 Lie algebras. So for simplicity, I'll just draw the picture for A1. For A1, there are no lower strata, and the moduli space of Acura is just the union of 2 nilpotent cones intersecting at the origin. So you can ask what this sort of description of the universal kernel of geometric Langlands is good for. Well, I certainly don't completely know, but I'll just make a couple of remarks that I easily can make. One is that if we had a description of T of G in which we could calculate explicitly and see all the symmetries, that would be an explicit answer for geometric Langlands duality. That statement, though, probably means that what is asserted in that sentence is out of reach. At any rate, in the descriptions I know, it's very hard to see explicitly the full G check times G symmetry. You can see a symmetry of G times the maximal torus in T, in G check, in G dual, or vice versa. And using this, you can use the theory T of G to compute the dual of a local system whose structure group reduces to the torus. You can do some more general things, but that's an example of what you can do. And you get something like the geometric Eisenstein series of Braverman and Gatesbury. So you could think of this as a quantum field theorist's way to motivate the construction of something like geometric Eisenstein series. I haven't thought about it carefully, but it's plausible you could do the reverse, use a knowledge of the G dual times T action to get the restriction to bun T of the D module over bun G corresponding to any local system of the dual group. Now, taking the liberty to perhaps go over time just a few minutes, I want to say a little about how Arthur's SL2 comes in. So let's go back to the classical equations in terms of the dual group, which were that we had a flat bundle with a covariantly constant endomorphism. So far, we discussed the obvious sort of boundary conditions in which we specified the boundary values of the fields. But the equations actually admit solutions with a pole along the boundary. And these solutions were important in my work with Gaiotto. So that's kind of why I thought that they're worth telling you about. So let y be a real function that's positive away from the boundary and vanishes on the boundary. So m is defined by y being non-negative. And by a pole, I mean that near y equals 0, sigma looks like b over y, where b is a fixed element of the Lie algebra. Well, if this is going to happen, b has to be nilpotent. And the reason it does is that sigma dual, is covariantly constant. So its characteristic class is independent of y. But if b has a non-zero eigenvalue, that eigenvalue is scaled when we changed y. And the characteristic class of sigma would depend on y. So the only way for a function like this to have a conjugacy class independent of y is that b has to be nilpotent. And conversely, when b is nilpotent, you can see that you can solve these equations with such a sigma, provided the connection behaves appropriately near the boundary. So I think we can interpret b as being, in some sense, the nilpotent raising operator of Arthur's SL2. But I don't know the most general statement, so I'll tell you something I'm a little bit more sure of, which is also closer to what Gaiotto and I were doing. So we'll specialize to the case where m is a 3-manifold times r plus. So at some points in the lecture, the 3-manifold was time times c. But if we do that, we do lose something. We fail to see that the theory is a topological field theory. But factoring out the r plus doesn't lose anything that I can see that we need to understand the category of branes and the usual story of geometric Langlands. Of course, we do lose the interpretation in 4-dimensional topological field theory. When we do specialize, the Riemannian holonomy of M becomes smaller, and therefore the twisting procedure, which involved embedding the Riemannian holonomy of M in the R symmetry group, leaves a larger unbroken subgroup. So when previously we embedded SO4 in SU4 in such a way that the commutant was SO2, which led to the Z grading of geometric Langlands, but now we're only going to embed SO3 in SU4, and the commutant will be not SO2, but SU2. So the SO2 that gives the Z grading of geometric Langlands is extended to SU2. And in fact, this is the SU2X or SU2Y that we discussed before. Which it is depends on what we picked for the nilpotent generator Q that we used to make a topological field theory. Now, once you've split off a normal direction from the free manifold, you can extend this complex endomorphism sigma to a triple of endomorphisms that transform in the adjoint representation of the combined group, SU2X times the dual gauge group. And I claim that SU2X should be identified as ortho as SL2. In fact, one can define a natural boundary condition in the G-dual description for every homomorphism of pi1 of C times SU2X to the dual group. That's essentially what Guyotto and I did, except that we took the homomorphism from pi1 of C to be trivial. But locally it's trivial anyway, but globally you can twist by the symmetries and do what I've just said. The way SU2X comes in here is rather interesting. Something happens that, at least to me, was a surprise. So Hitchin did not actually write down Nom's equations, but he mentioned them when he talked about Nom's treatment of monopoles. So a surprise to me is that these equations have a specialization that gives Nom's equations. And they have a polar solution that involves an arbitrary choice of homomorphism from SU2 to the gauge group. And that polar solution has had lots of applications in different areas. So to define a boundary condition on sigma, one asks that it should have the polar behavior just described. And this type of boundary condition is also important for Covenant homology. The rest of the boundary condition is trivial. You simply extend the chosen homomorphism from SU2 to the dual group to a homomorphism from pi1 of C times SU2 to the complexification of the dual group. By setting to 0 on the boundary fields that don't commute with the pole and equating the other fields to any local system on C valued in the commutant of the image of SU2. I guess that's what I have to tell you today.
Thank you very much for a beautiful talk. Are there any questions? I wanted to ask you about this SU2 action again. So they said there are two different SU2s.
Yes.
So one of them, you're saying, is manifests itself as a kind of Arthur's SL2.
Yes.
And it has to do, so it's not really geometrical. For example, one of the generators, say the kind of Cartan generator, responds to the homological grading.
Yes.
What about the other SU2? Is it one which we could see geometrically?
Well, in Hitchin's lecture, he explained a section of the Hitchin vibration, which actually is an A-brane. And one way to get that section here would have involved embedding the Nom pole, not in SU2X, but in SU2Y. So I don't claim this is a complete answer to your question, but that's an example of what you can do in an interesting way using SU2Y.
Right. But say in the context of this T of G theory
Yes.
that you talked about, is it true that one of the SU2s is realized more geometrically than the other?
Well, it depends on the description. There's a mirror symmetry between two descriptions. I didn't have time to explain it properly. Let's go back to the quiver. So when I'm going back to the quiver, I'm taking G to be of type A. There actually are also quivers of type B, C, and D. But I think my circles and squares are a little bit better here. So physicists associate to this quiver a three-dimensional gauge theory, which has both a Higgs and a Coulomb branch. But the definition of the Higgs branch is familiar to mathematicians, which is why you say it's more geometrical. And the description of the Coulomb branch is the kind of thing that people in my line of work have a lot of fun with, because it involves subtle quantum properties. So in that sense, your statement is right. There's a mirror symmetry that exchanges the two branches. This particular quiver is actually self-mirror. So here, T of A n minus 1 is completely symmetrical between SU2X and SU2Y in the sense that it can be realized in two different ways from this quiver. And the two descriptions are related by the exchange of the two SU2s.
So for instance, if we were to take A1 the
Yes.
A1 theory, right?
Yes.
So you mentioned that if we look at the space of vacua, it's going to have two copies of the nilpotent cone.
Right. Yes. So the A1 example was actually I think the very first example of ventriloquator in Seiberg. It's described by that simple quiver, which they argued to be self-mirror. And part of the argument was to precisely show that the moduli space was self-mirror. It was two intersecting A1 singularities.
But where do we expect to see the SU2s in this case? Let's say you have just two nilpotent cones, right? And they are connected at the origin.
Yes.
That is a precise description of
That's the description of the moduli space. Of course, if you you haven't made the question completely clear, but an example of what you could be asking is there something on which both SU2s act non-trivially?
That's right.
So for groups of higher rank, there's a simple-minded answer, which is that there are lower strata on which both groups act. But I don't think that's the right way to go in answering you. The right answer is to tell you the following. This isn't just a singular space. It's a family of vacua in a quantum field theory. And there's a lot we should say about the quantum field theory at any point. The most interesting point is the one at the origin. And if you're living at the origin, it's a superconformal field theory with all kinds of operators, many of which will transform under both SU2s. But anyway, even the ones that transform under one SU2 or another, their correlation functions will not factorize.
That's right. So in other words, the action of the groups is expected not on the space, but on the corresponding quantum field theory, which is much more complex than just the moduli space would indicate.
Yes.
Because of singularity, partly because of singularities, I guess.
The singularity is an important part as follows. In general, if you're at a smooth part, if you're an experimentalist, you usually want to know what happens at long distances, because that's what you can measure. And also, a lot of complications go away. After all, understanding what happens at short distances is usually described as trying to understand the laws of nature. So at CERN, they build an accelerator and try to make measurements at short distances, but it's hard to get to shorter and shorter distances. Whether we like it or not, anything we measure is usually at bigger distances than something else. So that's why I said at the beginning that going to long distances is more or less the universal problem of physics. But for mathematicians in geometric Langlands, there's no distance, but that actually means you're at long distances. I know you don't think about it that way, but take it from me. Now, at a smooth point, going to long distances can be adequately described by the classical geometry, but at a singular point it cannot be. And the singular points are the most interesting ones, as you might surmise.
Are there any other questions? Jim?
I mean, there is an interpretation of the other SL2. I'm not sure I don't see how it would be related to this, but the first SL2 is the Langlands operator.
Yes.
The other SL2 in certain situations is a monodromy operator. And it comes from the singularity, or it comes in the purely arithmetic situation. So I don't know what the relation with this would be, but it comes from the cohomology of the Kimura variety, where you have a place of bad reduction. And then there's the vanishing cycles of the cohomology, and the other SL2 is the uniform element of that, whereas the original one is a left-hand operator. And there is actually a kind of duality, sometimes called a layer duality, or relativity duality, which interchangeable.
For this class of examples? Or in general?
It's more in local, right?
One is local, the SL, not the SL2 you asked about is local, the other
yes.
is global. And there's this is, I think, probably a long way from what they're talking about.
Yes, but it's not something I can understand instantly, but there might well be a connection.
I think it's safe to say that this is a mirror symmetry that it's added to SL2s in some sense. That if we push all the analogies all the way, that should be connected.
And it is related to singularity, the other one.
I don't actually know what's interesting to do with the second SU2. The example I gave Edward when he asked, and a few similar examples, are all I've thought of that you can do that's interesting. But maybe if I knew more about what you're saying, one would think of something else.
Any other questions? Yes?
What's the hypercurrent manifold attached to the AN here?
Well, in general, for any G, the top strata, I zoomed by it very fast because I was running out of time, but in general, for any G, the top stratum, the two top strata are the two nilpotent cones. I wrote it here. So the top strata are one nilpotent cone times the apex in the other cone, or the apex in the first times the second nilpotent cone. Those are top strata in the sense that what they're top, they've either SU2X or SU2Y acts on as much as possible. And each of these strata are special because one of the SU2s doesn't act on it. Then you've got lower strata, which are products of orbits. And except for AN, Gaiotto and I did not completely determine which pairs of orbits come in. For AN, there's a well-known duality between orbits that flips a Young tableau. So that duality comes in here, but I don't really know what happens for other groups.
Any other questions? Well, if not, okay.
There isn't, well, you see, I wrote this very long paper with Gaiotto on the physics. I referred to it before, S-duality of boundary conditions in 2008. It hasn't, well, there isn't any written reference where one tried to digest it for mathematicians. A small part of what's explained is in a talk I gave, which has the title I don't remember exactly, but it has Nam and Bogomolny in the title.
Let's thank Edward again for a beautiful talk.